Hi everyone and Happy New Year for this new set of slides that I want to do and I want to talk about at some point the hydrogen atom. So I will briefly introduce what it is. Hydrogen atom and some peculiarities. Very easy. I will touch upon a couple of things and then I will give you an idea what it is. But before arriving to let's say any solution or any mathematical physical approach to this concept, I'll have to go through some basic math that I need to introduce before, which would be angular momentum, for example, and then possibly and then I will see what I forgot, because definitely I forgot something. But okay, so this is a G. So a hydrogen atom, what it is, we know. First of all, yes, so what is a hydrogen atom? So let's schematize in a simple way. We have a nucleus. We know what a nucleus is, I'll tell you in a sec. And we have an electron, okay? Nucleus and electron. So usually nucleus is made out of two things, protons and neutrons. Okay, now we know protons are fundamental particles. Actually they're not. Inside of protons we've got quarks. We'll get that maybe another time, but basically a proton is a collection of quarks, and it behaves like a single particle at certain energy, at certain scales when we look at it. But the good thing is that it's a positive charge particle, and meaning that it can attract negative charge particles, but thanks to electromagnetic force. Okay, what is a neutron? A neutron, let's do it like this, purple. Neutron, I will get you at the end of the slide. I will make a pause and then I will add some final remarks about the neutron, because now I forgot the exact composition, but basically it can turn, it's a neutral particle, so the charge is zero. It can attach easily to protons in nuclei. In fact, we have atoms because of the attraction between nucleus and protons. Okay, usually there are as many neutrons as protons. There could be more in isotopes, but let's do easy things. So for example, there will be a nucleus with two protons and two nucleus, and the other thing is the charge 2, and the other thing is that a nucleus can become a proton with some decay process, and this is the part that I will do at the end of the video, because at the moment it's a bit too technical and I don't have the basis to do that right now. But we have protons and neutrons, and they make, what do they make? We know what this is. Do they make an atom? Not yet. This is not an atom yet. We tend to call these ions because it's a charged particle. So this is an ion. It's an ion plus in this case. And how to make it an atom? An atom would be an ion plus electrons orbiting around. So if I add a charge here plus, and a charge and minus there you can see that the two charges, if they are of the same level, 1 and 1, they balances out, and the total charge is 0, and we can call this atom. This is maybe not the precise definition of an atom, but at least it's a definition that works for me at the moment. So let's keep it like this. So we have ions, no electrons, and electrons are fundamental particle. meaning that they cannot be broken, as far as we know, down into other particles. They are building blocks of what we think is made out of the universe. They have mass, they have spin, they have. We'll go through this in the future slides, but basically they are quantum objects that follows the Dirac equation. There are so many properties. I'm not going to list them, but basically we know from school that electrons are orbiting around the nucleus. They are the one that are exchanged between chemical reactions. If you think about valence band, valence bond, covalence bond, ionic bonds, things like that. I mean, there are. If you check your chemistry books, you will definitely remember a picture like something like this: a nucleus with some charge and some electrons around. And then the more complicated, I will tackle this. This, by the way, it's a hydrogen atom, one proton, one electron, and it's the easiest that I can do to describe the motion of the electrons. I won't describe the motion of the proton. I will keep the proton fixed, and then I will describe what happens to the electron around, hopefully, with the video. Okay, so enough as an introduction. So we know there is an L missing here. Sorry, nucleus, of course. Protons, neutrons, momentum. Okay, we are happy with this quick introduction. We know our basics and we know our target for the slides. So now, next thing I want to do, it's a little bit of math, and I will tell you why I need that bit of math, because I think it's interesting first, and it relates nice, and I will do another video possibly on symmetries as well, based on this piece of math. And it relates to symmetries and to rotating objects. Since in some sense we can say, we will see it's not exactly the same, but we can say that they are electrons, if you remember. Now picture your protons and picture the electron orbiting. We will change this point of view, but orbiting around the nucleus. You might have heard of this expression. This is much the same as when Earth is orbiting around the sun, right? So we have the sun, which is this thingy here, and then the Earth is orbiting around the sun. Maybe this is the correct direction, I don't know. Okay, and then we have this direction, this point here, and this distance here, velocity and distance. Okay, and the same can go for the electron. You can do the same with the proton and electron if you want, but let's for the electron proton we will see that this is not quite true. There is no, in quantum mechanics, there is no real orbiting around. It's a bit more fuzzy. I will give you the quantum description in the end. Not quantum, but this is true as far as we know. If we neglect general relativity, this is a description that we can do in classical mechanics with the Earth orbiting around the sun. And to describe a rotation, there is a very easy, compact way to do that. We just introduce a vector, okay? A vector which is like this, okay? Call L, angular momentum, and I will definitely have it wrong at the moment with the signs, but the idea is that this vector defines an orientation, and first of all defines a plane, okay? Because when you have a vector, you can define a plane, and you can say that the vector is 90 degrees with respect to that plane, 90 degrees. So there is one way to, and there are many vectors that are parallel to a plane. Think about if you manage to stick a pen on, it's very hard, but if you stick a pen on your table pointing up, this would be a vector that is parallel to your table. Or when you put a flag on the ground, it's sticking out like a vector perpendicular to the plane. Okay, and this is called angular momentum, and it defines a rotation, because you can say in this plane an object is rotating around this vector in certain direction. Okay, the direction is given, of course, by the velocity of the object. The direction, in this case, the object is moving from in clockwise direction. As you can see, it goes from left to right, and at a distance, because an object is, if it's rotating, you can think about any rotation that you have in mind. It's rotating around something, right? Rotation is usually rotating around something. So when you have a curve in your car, or your motorbike, let's say this is a motorbike, you rotate around the central point of the curve. You don't see it, but definitely who designed the curve must have done some calculation to understand what's the radius of curvature, how much is curve, how much is bend, if it's a U-turn, if it's an S-bend, or something like that. There are many points around which you turn, you pivot, you change your velocity. Okay, so definitely we have a direction of the velocity, and then we have a distance. The distance is very important, because if you let's keep an example. If you think about when you have a suppose you have a cord, a rope, and a heavy weight attached, and you want to swing it over your head, above your head. Okay, so you want to swing it above your head in this way, right? No, the hand up, and you want to swing it this way. You see that the cord now is tense, and the object is rotating, because you want to either fling it or whatever. Okay, if you want to do that, you have to be very careful about the length of the rope that you're using, because depending on which is it's easier if the length is shorter. You can do it with the wrist, but if the rope is very long, you need much more energy, but the velocity is lower, for example, for the same amount of energy, I think. So what I'm saying is that there are three different numbers that define a rotation, and I should change the title to angular momentum in a sec, because we are talking about, in fact, angular momentum now. Okay, the angular momentum is then defined by three numbers: velocity, distance, and actually there is another one, mass, because it's not by chance that, for example, in our solar system there are other planets that are smaller than Earth, and they are orbiting closer to the Sun. Okay, there are exceptions to that, but let's say this is the case, and they have they still have an angular momentum, but they have different mass, so their rotation will be different. Okay, suppose the case of the man swinging an object around his head. If the ball was twice as heavy, it would be totally different to make the exercise, let's say. So we have these three numbers that determines a rotation. Of course, a rotation, it's also a change in velocity. Okay, So rotation is naturally accompanied, attached to some kind of force, because if you think about when the Earth is here, the vector velocity is changed, right? You can see that he's pointing in a different direction. Maybe the length is the same, it's on the same plate, but at least something has changed. So also the angular momentum can define equation of motion. In fact, you can define F equal m per m times a. It's still valid when you have rotational motion. It's just that the equation of motion are different. I'm not going to write them now with the angular momentum, but the philosophy is the same. It's the math that is slightly different. Also, one other thing that I want to mention is that usually it's very easy to change coordinate system. This is something that I think I never talked about. Which I will maybe dedicate a future slides on it. But basically, you can coordinate system is, suppose you have an object, you define 3 axes, x, y, z, and then you want to describe the object with a position, and then you have 3 numbers, x, y, and z, and these 3 numbers defines the position in space. And if you want in time, this is a picture. You think about the picture of the object, so the time is frozen, time star, and then your object is here. Okay, and you have the position x1. Okay, of course you can also choose a different reference frame. For example, think about the picture above. I will remove Venus, I guess. I removed the sun, I removed the angular momentum. I wanted to do something easy. I will put the sun back in. No, the sun is gone. We have this reference frame. We have R. This is R. This is the number R. And then we have the angle theta. And then we have the angle phi. Okay, suppose the Earth is out of the plane. Okay, I hope this becomes R. R is this distance here, and then there are 2 angles. So the 3 numbers that defines is R, theta, phi, and theta, which are angles and a number. Latitude, longitude, and distance. But these are 3 numbers, 3 distances. Okay, you see that it's the same thing, right? It's the same ball described in 2 different ways. And this we can go from one end to another by some math, some matrices that I will maybe write you down at some point. Doesn't matter at the moment. I just want to let you know that there are these things in math, and we use at the moment. I'm not very fuzzy about this concept, but in physics as well. But the thing that is important is that angular momentum is usually best described in polar coordinates. These are called polar coordinates because rotation are easy with angles and radius of distances. Okay, not necessarily, not always, but just to let you know that most of the time when you deal with rotation, you change coordinate system to make your life easy. Okay, so enough. I want to get to the end of this first part of the video with something done, and that I hope you're not losing interest. There will be some quantum mechanics in the end and some classical and maybe a touch of relativistic quantum mechanics. I'm not quantum mechanics, relativistic physics. not very strong on that thing, so we'll just give just ideas. I think I won't go through the math. I need to refresh it. I don't have my books here, so let's keep it light. But yes, so at the moment I just want to remember that the orbiting electron around the protons that I described here is not really what happens, at least not what we know today. What we think it's happening is not this, but at some point in history there was the main leading atomic model, Thomson maybe, or maybe even after Thomson. Don't remember. Anyway, I will link it in Wikipedia so you can check the fact and the math as well. Okay, but angular momentum L is defined as this weird composition of number, mass times velocity, and then I will introduce this symbol x, and then the other number, let's see, d, distance. Okay. Sorry. Okay. So mass, we know that it is mass, usually kg, kilograms of the object. Velocity, we know what the velocity is. Velocity is the derivative of the space over time. We know what the derivative is, so we are not scared. It's a vector, and it tells you the change of position. So in this picture here, x1, x2 are two positions in two different times, and the velocity is the difference of these two vectors. Exactly that. If the distance is small, it can be an infinitesimal, as we know when the limits are involved, but we can also keep it light and use big delta and still have a discrete, let's say. We don't mind. It's a derivative. Mass, velocity, we know that. Distance, we know the distance, so you remember, I will do the Earth again here. Earth, there is a distance, which is the radius of the distance with respect to the Sun, and this is the distance d, and it's a vector because the Earth rotates, so the distance rotates as well, so it's a vector. And then there is this x vector, which is called vector product or cross product. Okay, so first of all, take two numbers, a and b. When I write a and b, usually there is a dot inside, a times b. In fact, two. If you do 2, 3, it's not 2 times 3, it's 23. But a times b is 2 times 3. So you have to remember that there is a dot inside. And the dot is what in school, at least I was taught, that 2 times 3 is 6. And we can still do the same. In algebra, the product, the x product but with numbers, it's replaced by a dot, and usually it's removed for simplicity. When you put back numbers, you do 2 times 3, which is 6 again, and that's it.